Alrighty, y'all. Today we're taking a look at homework 1 for Physics 211. And for this one, we're going to do some unit work, some math, and then we're going to do some 1D kinematics. And this is going to be a bit of a long one, so let's jump right into it. All right. So the first question we have these sneak peek questions. Question 1, we're given the acceleration of gravity on Earth is 10 meters per second squared, and we want to convert that into kilometers per minute squared. All right. So I'm going to write, so I have 10 meters per second squared. All right, I'm going to write that in a special way. So my numerator units, all right, which is my meter, and then I divide by kind of my denominator units. All right, I have meters in the numerator per second squared. I'm just going to write it like that so that it works out. I could also just put the 10 out in front. All right, but the important part that I want is to have this kind of unit fraction, because then what I can do is I can multiply by 1 in some helpful ways and convert the units. That's how I like to do my unit conversions. All right, so let's start by converting this meters into kilometers. So I know that 1,000 meters equals 1 kilometer, right? And if I were to divide both sides of this equation by 1,000 meters, right, I would end up with, well, 1,000 meters over 1,000 meters. Well, that's something over itself, so that's just going to be 1 equals 1 kilometer over 1,000 meters, right? So what this is telling us, right, we did something like this in recitation as well. What this is telling us is that I can take this fraction, I can take this number, and multiply it by 1 kilometer over 1,000 meters. And since I'm just multiplying by 1, it's not going to change the value that is being represented by these units. It's just going to change the units that are being used to represent that value. And it'll still be the same acceleration physically. We're just describing it in a different way. So what I can do is I can multiply by 1 kilometer over 1,000 meters, which is just multiplying by 1, right? And there's a reason that I chose to divide by meters instead of kilometers, and that's because using this fraction, now I have meters in the denominator and meters in the numerator. So what that's going to do is just going to cancel them out for me. All right. So we've gotten rid of meters. Now let's get rid of these pesky seconds. All right. So I can do the same thing. I know that I want seconds in the numerator because I have seconds in the denominator over here. So I'm going to say, all right, 60 seconds. I'm trying to convert that because 60 seconds is 1 minute. That's what I'm trying to convert that into. Right? And my seconds will cancel with, well, here I have seconds squared, so it's only going to cancel with 1 of them, and I'm still going to have 1. So I have to do the same thing again, right? 60 seconds times 1 minute. Right? Seconds will cancel with the rest of that. Because then I'm left with the remaining units that didn't cancel of kilometers, minutes, or kilometers per minute squared, right? This would be the same thing as if I took my value, right? This here would be the same as if I multiplied by 60 seconds over 1 minute squared, right? Because there's my seconds squared, there's my minute squared, so my seconds squared would still cancel, and I'd be left with minutes squared. The only difference, I like to do it in these individual steps because I always forget when I'm multiplying across that there's 2 there. It's personal preference. Both work perfectly well. It's just whatever you prefer to do. All right, so multiplying across, I have 10 times 60 times 60. 60 times 60 is 3,600 times 10 divided by 1,000. That should be 36 kilometers per minute squared. Right? That's my answer to the first one. Right. So now moving on to number 2, we have a couple of curves and we want to find where they intersect. So my first one is y equals 4 and my second one is y equals 6x minus 5x squared. So the first thing I want to do, just to visualize this, I'm going to graph it. So I graphed this on Desmos ahead of time. All right, so I have my y equals 4 there, and I'm just going to use some values. So to find my, I'm going to find my x-intercepts just real quick. So I'll say when y is 0, not 5x, sorry, that's 6x minus 5x squared. I can factor out an x, so I'll get 0 is x, 6 minus 5x. So I know that x equals 0 is a solution, right, to that equation. So that I know that when y equals 0, because that's what I set there, x can also equal 0. And then also this will be a solution. Sorry, I'm just kind of brushing through this algebra a little bit. Now I have to remember how to solve for this. So 0 equals 6 minus 5x. So 6 equals 5x. X equals 6 over 5. 6/5, that is 1.2. Right? And just to save us the algebra a little bit, I'm going to skip to the end because I graphed this ahead of time on Desmos, and just give us our approximate apex is going to be at 0.6 and 1.8. All right, so like that and like that. Now, looking at these curves, it doesn't look like they intersect. All right, and I could be wrong. I could have graphed it wrong, so we're going to check it with algebra anyways. But I wanted to graph it to visualize where should I be expecting them to intersect, and in fact, we're expecting our solutions to be imaginary. All right, so to do the actual algebra and find those imaginary intersection points, all right, I have y equals 4 over here, so I can take that 4 and plug it in for y on this equation. So I'll have 4 equals 6x minus 5x squared. And I always like to rearrange it so that my highest degree is positive. All right, so I'm going to take this and I'm going to add 5x squared to both sides of my equation. And I'm also going to subtract 6x from both sides of my equation. All right. So what that's going to do is it's going to cancel out my 5x squared on this side and my 6x. So I'll be left with 5x squared minus 6x plus 4. All right, because I have a plus 5x minus 6x plus 4 on my left side equals 0. All right, because I cancel out all that. Right? Now, you may be recognizing that this is a quadratic of the form ax squared plus bx plus c equals 0. Now I know that I have a negative thing here, and oh, shouldn't it be minus b? But our general form of the quadratic is plus b, so when I plug into the quadratic equation, I can plug in a negative number for b, and it'll all work out because I assumed that it was positive at the beginning, and things might go wrong otherwise, because then I'll be double counting for that sign. So, knowing this, I'm going to remember my quadratic equation. If you don't have it memorized, you can look it up, but it's a good thing just to keep in your back pocket. So it'll be negative b plus or minus the square root of b squared minus 4ac all over 2a. I'm just trying to write it so it's legible. All right. And this will give me, right, I have this plus minus here. So one of my values of x will be plus, one of my values of x will be minus. So plugging in my values, right, up here I have a equals 5, b equals negative 6, and c equals 4. So plugging that in, right, I have negative b is minus 6 plus or minus the square root of b squared minus 4 times A times C all over 2, and A was 5. To keep checking so I don't forget. All right. Now, this looks a little gross, but we're going to start breaking it into chunks, breaking it into pieces. So the first thing I have in here, I like to start inside my parentheses and start smushing some of these together. I have 4 times 5 times 4. All right, so 5 times 4, that's 20, times 4, 20 times 4 is 80. And then I also have 6 squared, or negative 6 squared, so it's 36 minus 80. I'll be writing these down as well. I have minus 6, so that'll leave me with a positive 6, plus or minus square root of, we said that was 36 minus 80, all divided by 2 times 5, 10. All right. Now I can see 36 minus 80 is clearly going to be a negative number, and I can't take the square root of a negative number without getting something imaginary. So I will have 6 plus or minus the square root of negative 44 all over 10. And there's my negative number. I can't take the square root of a negative, but I can simplify it a little bit. All right, this is getting more into algebra. Now that we've noticed it's imaginary, I know my curves don't intersect. We've confirmed that with the graph as well. But this is just a little bit of algebra for you. All right, so I'm going to split my numerator as well and simplify 6 over 10 to be 3 over 5, plus or minus. Then inside my, underneath my square root, I'm going to factor out a 4. So I'll end up with square root of 4 times 11 times negative 1. All right? And because it's multiplication under my square root, I can distribute that and split it up. So I'll have square root of 4 times square root of 11 times square root of negative 1. So square root of 4, that's going to be 2. Well, in 2 over 10, that'll simplify down to 1/5. So I'll have square root of 11. Square root of negative 1 is I, an imaginary number. And there's my 1/5. So not the answer we were hoping for, right? It's not a clean number where we get that x equals 3. Right? But we do a little bit of imaginary algebra there. Just remembering that the quadratic formula is something that'll be pretty useful and something that we might want to keep in our back pocket for use later. Right? On to number 3. The area of a triangle whose base is 3 seconds and whose height is 6 meters per second. So I'm going to draw myself a little triangle. It will not be drawn to scale, because I know I have rectangles, but I'm running out of space. Rectangles, squares, grid, that's what it is. I have a grid paper, but graph paper, but right, so with a base of 3 seconds and a height of 6 meters per second. And I want to find the area. And I know that the area of a triangle is 1/2 base times height. So all I have to do, I'm plugging in my numbers again. 1/2, my base is 3 seconds, and my height was 6 meters per second. So I'm going to start by multiplying the numbers, and then I'll multiply my units. So it'll be 6 divided by 2 is 3. 3 times 3 is going to be 9. And then it'll leave me with meters per second times seconds, because I have my units to deal with. And I can simplify my units a little bit because I have meters in the numerator, but then I have seconds in the numerator being multiplied in, and seconds in the denominator over here. So that'll cancel and leave me with 9 meters. Okay. Now we're going to use that fun little fact when we look at question 4, because now I'm looking at the area of the shaded region. Well, the shaded region has a base that is in seconds and a height that's in meters per second. So my first area, this triangle here, it'll be 1/2 base times height. So I'll call that A1, right? and my base will be 2 seconds. So I'll put this 1/2. My base is 2 seconds, and my height is 3 meters per second. Right. So my 2 divided by 2 times 3 is going to be 3 meters. And I know it's meters because, again, it's meters per second times second, and we already did that down here. And my area 2, that one's going to be, this one's just a rectangle, so it's going to be 2 along the bottom, 2 seconds, and 3 meters per second for a height. Okay, so 2 times 3, that gives me 6 meters. So if I'm trying to find the total area of that shaded region, A1 plus A2, 9 meters. Okay. Now it's asking us what is the physical interpretation of the area of that shaded region. Well, our hint is in the units, right? Meters is a unit of length, right, or distance, right? So my velocity versus time graph, I take the area under the curve, and it gives me my total displacement, how far I've traveled, right? And it's measured in meters, and we know this as well for my friends who have taken calculus. And we know that velocity is the derivative of the position versus time graph. So the integral of the velocity graph, or the area under the curve, is the position. Okay. So all of this is leading us in with a little bit of math so that we can do the rest of these kinematics problems. So onward we go. Our first problem, we have a car that gets distracted by some physics students and veers off the road, and we crash into a cactus. All right. The driver is wearing a seatbelt, which is excellent because you always want to be wearing a seatbelt in case you get in a car crash, because that's not good. And we're decelerating from 120 kilometers per hour to a dead stop in 50 milliseconds. All right. And what we're going to be calculating, we're calculating our acceleration of the driver as it comes to a stop. Now, like it says, we're given some numbers, 120 kilometers per hour and 50 milliseconds. We don't want to plug in numbers until the very last step. I will always recommend this. We want to do all of our algebra with variables and letters and plug all the numbers in at the end, because it's harder to lose variables that way and harder to like accidentally drop numbers, solving for these intermediate quantities and all that stuff, right? It's a lot to keep track of if I plug the numbers in, but if I keep it all in terms of variables and plug in at the end, maybe something will simplify for me as well. Right? So we have to first figure out what variables we're going to use to represent them. When I'm doing a kinematics problem, I have some variables to choose from. I have my initial position. I have my position at the time t. I have my initial velocity. I have my velocity at the time t. I have my acceleration, and I have time t. All right? In terms of what we know, all right, I have 120 kilometers an hour and 50 milliseconds. Well, my first hint, 50 milliseconds, that's a time. So that makes sense that my variable down here would be my 50 milliseconds. Okay. And my other 120 kilometers per hour, well, kilometers per hour, that's a distance per time. Distance per time, that's a velocity. The only problem is I have two different velocities. Oop. iPad's freaking out. I have two different velocities to choose from. So what we have to do, we have to revisit the context of the problem, figure out, is this my initial, is this my final velocity? So our hint is that we're decelerating from 120 kilometers per hour to a dead stop, which means that I'm starting at 120 and then I end up stopping. So that tells me my 120 kilometers, that's 120 kilometers per hour, excuse me, is my initial velocity. Now, before I do anything else, I want to convert these units into base units. Our base units in metric are meters, seconds, kilograms. If I keep everything in terms of base units or like derived units like newtons or joules like we talked about in recitation, then I'll still carry my units through my equation, but I know that things are going to work out and it's just one less thing that I have to really focus on. So, same thing I did before. I'm just going to rewrite this so it's a nicer fraction for me to work with. All right, in order to convert these units, I'm going to get rid of kilometers first. So I'm going to do times, all right, so kilometers in the numerator. So 1 kilometer is 1,000 meters. That's how I can cancel kilometers. And 1 hour is 3,600 seconds. Now I could also say that 1 hour is 60 minutes and 1 minute is 60 seconds. All right, it'll work out the same. I can do that real quick. 60 minutes and 1 minute is 60 seconds. All right, because then my hours cancels and my minutes cancel. And there's my 60 times 60, which is 3,600. All right, so it all works out the same in the end, and I end up in units of meters per second. All right, so figuring all that out, that's going to be 100 over 3 meters per second. I like fractions because I don't like rounding, but if you like decimals, it'll be 33.3 meters per second. Right? So now I can completely ignore that 120 kilometers per hour number, and now I have my answer, or I have my initial velocity in meters per second, and that's what I'm going to use for the rest of the problem. Now let's deal with this milliseconds. All right, so milliseconds is in my numerator. So I'm going to multiply, I'm going to say that 1,000 milliseconds is in 1 second. Milliseconds goes away, and I'm left with seconds. So it's 50 over 1,000 seconds, or 5 times 10 to the negative 2 seconds. Or if you don't like scientific notation, that's 0.05 seconds. All right, all different ways of representing the same thing. All right, so we're going to be using this for our calculations. Again, now that I've converted it, I'm not going to use this number at all. I'm just going to use my base units number. Cool. Onward, now we want to write an expression that gives the velocity of the car as a function of time in terms of acceleration and initial velocity. So that's just going to be our kinematics equation. Our v of t is v naught plus at. And now we have to think about the physical moment that corresponds to time t equals 0. When it's asking about the physical moment, that's thinking in the context of the problem, how do I know that the problem is starting? Right? Now we've talked about that we can only use these kinematics equations when I have a constant acceleration. If I'm thinking about what the car is doing, the car is driving down the road first, right? It has to veer off the road, but the car is driving down the road. Then it veers off the road, crashes, and decelerates. So while I'm driving, my acceleration is 0, because I can assume I'm just driving at a constant velocity for a little bit. Then it veers off the road, weird things happen. But the second that it starts crashing, the second it hits the cactus and starts slowing down, we're told we're assuming that it's a constant acceleration because we're calculating that constant acceleration. Right? So I know that because I have to find the chunk of time in my problem that has the constant acceleration, that's where I define the start of my constant acceleration has to be the start of my problem. It has to be when t equals 0 so that I can use these kinematic variables, or the kinematics equation, sorry. All right, so t equals 0 when the car crashes and I did not leave myself enough space to write this. And the driver starts to slow down, right? Once the driver starts slowing down, that's when our problem starts. That's when our t equals 0. Because that's also when our velocity, right, at t equals 0, our velocity is 120 kilometers an hour or 33.3 meters per second. And because that's our velocity at t equals 0, that's why we call that our initial velocity. Right? All right. Part C. I was about to say part 3. No. Part C. All right, we discussed in class that we can use these kind of phrases in a question in terms of our algebraic variables. This is kind of our translating step of getting all of my word problem into the algebra that I'm going to actually solve, right? So our question is, what is the value of blank such that blank is equal to 0 at time blank? Well, all of these questions that I'm going to be formatting will start with, what is the value of blank? What this blank is, it is what is the question asking me to solve for, right? In the end, I'm going to find an answer. Let's say it's some problem, and I say, okay, my answer of this problem is x equals 4 meters, and I circle it. So when I'm filling in this blank, what is the value of blank? I want to know, what am I going to solve for and circle at the end, right? What variable represents my answer? In this case, I circled it. I already circled it up here. I'm solving for my acceleration. And the variable we use to represent acceleration, I'll make it red so it stands out in the text, is a, right? So what is the value of a such that blank is equal to 0 at time blank? Now the rest of this phrase, the rest of this question, right, that's just trying to get us to figure out, how do we define our variables such that this is the situation that we have, right? So I'm going to solve for the value of a such that the thing that is happening in the problem happens. So it's kind of, how do I know that I'm getting where I'm going? How do I know that I'm at the end of the problem? Well, we're given that my initial velocity is that, and I know that I come to rest or come to a dead stop after 50 milliseconds. So the way that I know that I'm at the end of my problem is the part where it's at a dead stop in 50 milliseconds. We need to figure out what acceleration would cause that to happen. Well, how do we say dead stop? Saying the same thing over and over, right? But my velocity at some time, right, is equal to 0. Right? What has to be 0? At a dead stop and it's not moving, my velocity will be 0. And that happens at a time, 50 milliseconds. But again, I'm just going to use my 0.05 seconds. Right? So it's, what is the question asking for? What is the value of blank? And how do I define the context of the problem? How do I know that I've succeeded? How do I know that this is the right acceleration? Well, it causes the velocity to be 0 after 50 milliseconds, which is translating to a dead stop in 50 milliseconds. Right? So onward we go. The rest of question 1. All right, we're on to part D. Now we want to write an algebraic statement that corresponds to the sentence that we wrote and solve it for the acceleration. So before I had my kinematic equation, v of t is v naught plus at. Right? But now we want to say, okay, what is the value of acceleration, right? We're going to solve this for acceleration. And then eventually we're going to plug in some numbers. All right? But first we're going to solve this for acceleration. So I'm going to subtract v naught from both sides. So I'll get v of t minus v naught equals at. Then I can divide both sides by t, and I'll have let me write this in a normal color. V of t minus v naught over t equals acceleration, right? Now, we're going to plug in our numerical values and find our acceleration, but make sure we're retaining our units. That's why it was important that we converted all of our units before, so that when I plugged in here, it makes things a little bit easier. Right, so my v of t, my velocity at time t, we said that was 0. As you can say, that's 0 meters per second. Then my initial velocity, it was 33.3 meters per second. And my time was 0.05 seconds, right? And that equals my acceleration. Now that 0, that can just disappear because it's 0. And what this is going to end up giving me is minus 33.3 meters per second divided by 0.05 seconds is acceleration. And we can check to make sure this makes sense, right? My units, all right, now I'm going to end up with meters per second over seconds, which is the same as saying meters per second times 1 over seconds, right? Dividing is the same as multiplying like that. And if I multiply across with my fraction, I'll end up with meters per second squared, which we can recognize as our unit for acceleration, right? So using that, I have my meters per second divided by seconds should give me a unit of acceleration. So the last thing is punching this into a calculator, and we're going to get that my acceleration is minus 666.67 meters per second squared. All right, and like I said, what is the value of blank? What am I going to circle? I finished my problem and I circled my acceleration, right? I answered the question. Now, we have encountered some minus signs in my algebra. We have this negative acceleration. What is the physical significance of that minus sign? Because remember, we're not just doing math anymore. We're doing physics. And math is the language of physics, but in the end, we're using the math to communicate a physical quantity, right? So, I kind of did this without even noticing, but my initial velocity, I said, was positive, right? So I said that if I have my car driving along, my initial velocity going that way, I said that that way was positive, right? Because I said my initial velocity was positive, and I know that my velocity is decreasing, right? It goes from a positive number to 0. My change in my velocity is going to be negative, right? My velocity, because it's positive and decreasing, the change is negative, and acceleration measures the change in my velocity, right? Had I said this was a negative velocity, right, I can see that that negative would cancel with this one, so I'd end up with a positive acceleration. But it's still communicating the same thing. It's just saying that, oh, had I said that this way was positive, because I can pick whatever coordinate system I want, then I would have had a negative initial velocity, and since it's decreasing, since it's that negative velocity would be getting less negative, right? It would be still going towards 0. My change would still be positive. So an important point to note, when we're thinking about a positive or a negative acceleration, we're not thinking of accelerating or decelerating. If it's speeding up or slowing down, we're thinking about, are my velocity and acceleration in the same direction or opposite direction, right? So, a quick little thing. If my velocity is positive and my acceleration is negative, right? That's going to tell me that my magnitude of my velocity, right, I'll be slowing down. That's what we saw here. I had a positive velocity before, right? I had a positive velocity and I was slowing down, so I got a negative acceleration. Right? If I had a positive velocity and a positive acceleration, that would be speeding up. Right? It's the opposite. Now, if I have a negative velocity and a positive acceleration, that would be slowing down, right? Because it's going in the negative direction, but it's changing towards the positive, so it's getting less negative. It's moving back towards 0, so it's slowing down. If I have a negative velocity and a negative acceleration, it's going to be speeding up, right? Because again, if I'm moving in the negative direction, if my velocity is negative and the change in velocity is also negative, it's going to increase it and make my velocity more negative, which means it's going faster, just in the negative direction. All right. Moving on to question 2. The previous problem we solved for an acceleration. How many times greater is this acceleration than gravity, the acceleration from an object in free fall? All right. So we're going to do this. We're going to retain all of our units and manipulate everything the way we normally do. So since we're talking about how many times greater, I'm going to do this based on the magnitude. So I'm going to take the absolute value of the acceleration that I just solved for. Ooh, I need to keep that units. All right, I'm taking the absolute value just so that I can compare how big it is. Because remember, that negative sign, it just tells me the direction that it's going. All right, gravity, my acceleration from gravity, could also be going in the negative direction. So that's why I'm just taking the absolute value, so I don't have to worry about the signs. All right, and if I divide this, that should be meters per second squared, my bad. If I divide this out, right, I have meters per second squared divided by meters per second squared. So all of my units are going to cancel. And my number is going to end up being 68.0272108844, right? And because all of my units canceled, this number is unitless, right? Which we see sometimes when we have a ratio between two things. This tells me that the acceleration of the driver crashing the car is 70 times greater than the acceleration of an object in free fall. Now, this is a very surprisingly large number, but it doesn't surprise me as a result of crashing the car, because crashing a car is dangerous. So if you're accelerating that extremely, you might break some bones, which is why you wear your seatbelt. All right. So this video is getting a little bit long, so we're going to split homework 1 into 2 videos. So I hope you found this video at least a little bit helpful. And let me know if you have any questions about this or anything else that you want me to try to explain. And I will do my best to try to explain it, because I guess Sydney explains stuff.